All right, we were supposed to start with from dehydration. Now, dehydration in the case of alcohols is a proper elimination reaction. Why? Because we take a complete small molecule out of an alcohol, that is water, and we form an alkene. This happens under catalyst and heat. We did the same thing with the help of concentrated sulfuric acid back in IGCSE, but now we can use aluminum oxide or alumina or pieces of porous pot or pumice. We can use all of those. This is possible. Now, when we go with this reaction, I always ask my students to write the stuff a little bit differently. So it's easier for you when they try to give you some bigger alcohols or not just ethanol or propanol. You'd know how to behave or how to take the water molecule out and convert the rest into an alkene. Take a look at this. We usually write it as CH3CH2OH. We don't usually write it like this when we are trying to convert structures of reactants into molecules by taking elimination. So what we do commonly is that I tend to do it like this. I tend to write the functional group below the structure. And then what I do is that I decrease the number of hydrogen atoms by one in the adjacent carbon atom and write H over there. I completely take out the molecule, and in between these two carbon atoms, I add the double bond to form our alkene. That's how it works. So if you have some other alcohol, let's suppose you have this, right? You have this, then you can form a water molecule out of it. So since there are two adjacent carbon atoms, you can take either one of the hydrogen atoms. I mean, whether you take it out from the left or the right. Cambridge tends to not specify this for elimination reactions in their papers. If you take a look at the past decades papers, so you'll get an idea that if even if I don't, I make it CH, I write H over here, you take the whole water molecule out. This is where you're supposed to put the double bond. There you go. You have the butene as a molecule, as a resultant alkene with you along with water. So this gives you a pretty good idea how to do it. Remember, the rest of the structure, there won't be anything happening to the rest of the structure. Only the carbon which has the functional group and the carbon next to it, which I'm calling adjacent carbon atom, will have the difference and will have the double bond in between. I hope you get the point. Okay, so moving on, this reaction is something that we did back in IGCSE in detail, and we do the same thing over here. This was a very common question in past 5 years of IGCSE papers. This is again a common question over here too. The diagram slightly differs in what we've had back in IGCSE and what we have over here. So even if it does, it's not such a big problem. Let me clarify a few steps and let me clarify the differences as well. Yeah, we just took ceramic or mineral wool and we soaked it in ethanol before we put it over here. We never used direct ethanol because of the safety reasons. I hope you understand that. A little bit of a yellow arrow over here or a red arrow over here, which means usually warm over here and strong heat over here is understandable, but that was in just one or two books back there. It's not a part of any of the A-level books. We usually only strongly heat the pumice or the sport pieces, aluminum oxide powder, aluminum, whatever you'd like to call it, whatever the catalyst is, and we heat it. And there is then a delivery, and delivery is over water. Remember, this is ethene gas. Ethene is insoluble in water, and hence, like all other deliveries over water for gases, we go for the same with ethene. We did that back with another alkane or alkene during cracking. We did that with hydrogen during cracking or other processes that produce hydrogen. For example, metal and acid reactions back in the chapters had the same thing. So I hope you understand that only insoluble gases are taken as a delivery over water. The first test tube is usually rejected because it has impurities that air involved with it. The later on the test tubes that we use are usually the pure ones, so we can go with this. Delivery over water is good for insoluble gases because they simply rise up. What happens with water is that we are good with this because if there is any dust particles that go along with the gas, water usually traps that. Being solid, it settles down at bottom, and only the gas rises up in the tube. So that's a very good way for to perform this experiment. I hope you get the idea. Moving on, oxidation. Now, usually alcohol can be classified in primary, secondary, and tertiary, and for the most of the reaction, it really never made any difference whether we are dealing with primary alcohol or secondary or tertiary. The type of products formed were usually the same, and we can generalize the homologous series, but oxidation and reduction are the reactions which the cycle compounds that we commonly talk about are different. So, in case of oxidation of alcohols, the primary, the secondary, and tertiary alcohols are going to behave differently. We need to go for a test for this, and there are a couple of things that you should write in the book. They won't be mentioned in the book. First things first, primary and secondary alcohols are the only ones that we can oxidize by using a strong oxidizing agent such as potassium dichromate 6 in acidified form. We usually acidify it with dilute sulfuric acid. Tertiary alcohols are not oxidized at all by any of the strong oxidizing agents, be it acidified potassium dichromate 6 or acidified potassium manganate 7. So the test is going to come out positive only for primary and secondary alcohol. Now, as soon as I say the name acidified potassium dichromate 6, I hope you understand the color changes because we are familiar with its orange color at start, we are familiar with its green color at the end. The orange color at start is because of the dichromate 6 ions. The green or the gray green appearance is because of the chromium 3 ions. So these are the colors that you're already familiar with back from IGCSE. So I hope you understand what the starting and ending resulting colors would be. So the product formed when you attempt to unoxidize an alcohol can be used to distinguish between primary, secondary, and tertiary alcohols. Remember this, with tertiary alcohols, a mixture of tertiary alcohol along with our acidified oxidizing agent, when warmed, no reactions take place. So yeah, the orange color would remain same, orange. For a secondary alcohol such as propan-2-ol, a ketone is going to be formed with a similar process, acidified oxidizing agent, a little bit of warming, and of course the color change would be there accompanying orange to green. Uh, the same thing would happen with primary alcohol, but this time the product would be an aldehyde such as ethanol is oxidized to ethanol. Since we are familiar with these reactions, so it shouldn't be a problem. We already know how this proceeds. Okay. So if you're going to do that in lab, and yes, that's a very good test in lab, this whole activity, this is commonly known as Lucas's test, right? So Lucas was the name of the scientist who did that. So I think it's pretty easy. In many of the past papers, you're going to find specifically the ones beyond 2016, the word Lucas mentioned. So as soon as you see this word, understand we're talking about the distinguishing test between primary to secondary and tertiary alcohols. You can see the orange color, you can see the two green colors. So it gives you a very good idea how you can proceed with it. Okay. And remember, since we know that the oxidation is pretty much a cyclic process among these homologous series, a few of them that we discussed, starting from all the way from alkenes. I hope you remembered that when we used alkenes and we converted them, oxidized them into alcohol, and now we know we can oxidize an alcohol into an aldehyde and an aldehyde into a carboxylic acid. So the detail for what I'm just writing is given right over here. If we have excess of acidified potassium dichromate 6 and we are fluxing it, we'll definitely not stop at ethanol. The ethanol would be converted into ethanol and the ethanol would be converted into ethanoic acid. So this is a cycle. I hope you understand. If we go with oxidation up top every time, we can go from left to right in this reaction. And if we go with reduction every time, we can go with uh, right to left every time. A few of the reduction reactions are something that we haven't studied yet. Don't worry, this chapter and the next chapter, whatever reaction from the cycle we haven't studied yet will be considered. But that should give you an idea. Now, keep in mind that alkenes were capable of being oxidized directly to carbon dioxide as well. Alkenes were capable of being converted into alcohols, specifically if we're talking about secondary alcohols, and those can be converted into ketones, right? So I shouldn't be actually using. Okay, so there are other possibilities as well. Remember, even for this specific one, the further oxidation can give us carbon dioxide. Remember, carbon dioxide is an ultimate oxidation product. And we actually directly jump to carbon dioxide if we use any of these, if we go for the combustion reaction. Now, combustion is actually a reaction with excessive oxygen. We're not using an oxidizing agent, whether strong or weak, that's not the discussion. The discussion is we're directly using oxygen. So that's carbon dioxide. So remember, in any of these cases, you may not have the carbon's oxidation state as its maximum, which is +4 in the case of carbon dioxide. So that's understandable that carbon dioxide can be the ultimate product of oxidation. Even if you're going with this whole chain, at the end of it, yeah, you'll get that. So any of these products can be converted into an ultimate product, carbon dioxide, upon burning. I hope I make sense when I say this. Well, even if I don't make sense with the reduction reactions, don't worry, we haven't studied them yet, and we'll study them a little later in chapter 18. Moving on, carboxylic acid. Now, they are going to keep carboxylic acid and its topics very small and to the point. We have already studied and discussed esters, their naming, their structures, or some of their reactions, such as uh, hydrolysis. Now, moving on to carboxylic acid, the first reaction they're trying to go with is the one that is different that you haven't studied yet. So carboxylic acid was a topic back in IGCSE. We discussed them as acids. We discussed them that we can use them, and we specifically discussed their esterification reaction back in IGCSE. Now carboxylic acids formation have been discussed from alkenes or from alcohols or from aldehyde all the way to carboxylic acids in these reactions of oxidizing agents using potassium manganate 7 or potassium dichromate 6. So whatever written in this first paragraph is something we have studied in chapter number 15, 16, 17 continuously. So you have the idea. Now, carboxylic acid can be made by one more way. We discussed that back in chapter number 16, but we haven't really discussed the details. So let's discuss it. Carboxylic acid are made from nitrile. When a nitrile is refluxed to dilute hydrochloric acid, hydrolysis occurs and we make the acid. Now remember, we have studied that we can also go with this hydrolysis with an alkene, not with an acid. And in that case, it would be different. We're not going to produce the carboxylic acid. Instead, we are going to end up with its sodium salt. But we tend to go with forming carboxylic acids, and that's how the reaction goes. Now remember, the usage of nitrile was to increase the number of carbon atoms in the chain by one. So if you're talking about propane nitrile being converted into propanoic acid, remember we might have started from something smaller over here, right? So let's talk about this. Use a multi-step reaction and convert ethene into propanoic acid. How would you do it? Take a minute or two, think, let me know your answers. For reminding, the pH values are going to be closer to 7 being a weak acid. So you get the idea. Apart from that, there were three characteristic acid reactions. Acid plus alkali gives us salt plus water. Acid plus metal gives us salt plus hydrogen. Acid plus carbonates or hydrogen carbonates gives us salt plus water plus carbon dioxide. So you have those reactions in front of you. This clearly gives the idea of the same reactions we studied back in IGCSE. Moving on, last would be reduction reaction. It's the exact reverse, and we can convert a carboxylic acid into an alcohol. Saying that we can convert it into an aldehyde and then the aldehyde into an alcohol would be a much better way of saying it. But since the book hasn't described the aldehyde chapter, so the book tends to skip that step over here. And you'll find the step in chapter
Sir,
number 18. All right? Jisad, आप
yeah,
कह रहे हैं?
sir, we always need 4 hydrogen for the reduction of carboxylic acid. Always?
Yeah, in most of the cases, you're going to do the same beta because if you take a look at it, you are going to convert it into an aldehyde and then into a primary alcohol. Since this is a double step reaction mentioned over here, so of course, the carbon that is bonding doubly to the oxygen would be converted with 2H, and the oxygen we're going to take out will form water molecule. So yeah, 4 over here is actually two of these and two of these, if I be straight.
Okay, sir, got it.
And since every COOH would, my bad, every COOH would be converted into COH, and we're going to add up H2 over here. Plus, there would be water, and we're going to add up this H2 over here. So, yeah, 4. I hope that makes sense. If we are talking about double reaction, we're talking about directly converting it into an alcohol. Okay. So moving
Yes,
on,
sir.
um, primary alcohols will be converted from carboxylic acid. Remember, you can't do it into a secondary alcohol. Ketones are converted into secondary alcohols. The reducing agent we're going to use is lithium tetrahydroaluminate, LiAlH4. Remember, it was the more uh, stronger reducing agent. It can work at room temperature, it works under dry conditions. In non-aqueous conditions, hence we use ether. This is dried because it reacts violently with water and it reduces water into OH negative and H2. We use the symbol H just like we use the symbol O in oxidation reactions, giving an idea that it was a reduction reaction. It is a reduction reaction in this kind of conversion because we take oxygen out of it as well as we add hydrogen to it. So in both terms, it can be regarded as a reduction reaction. Don't forget the conditions for LiAlS4, that's important. And this finally